1.6 Discontinuities. Well, a discontinuity is whenever a graph is not continuous. In other words, if it's continuous, you can draw a graph without picking up your pencil, without any jumps or holes or gaps or anything like that. And if it has a hole or a jump or a vertical asymptote, those are all discontinuities. So we can be the different types of discontinuities can be classified as, whoops, helps if I'd switch to the writing utensil first. A jump discontinuity, which happens when we have like a piecewise function. We could have an infinite discontinuity, and an infinite discontinuity is a vertical asymptote. Vertical asymptote. And that happens whenever we have a non-removable discontinuity. So non-removable is another way to describe infinite. Non-removable. Or we could have a removable discontinuity, and a removable discontinuity is when you see a hole in the graph. So this one right here is a removable discontinuity. Means you factored something out and canceled, and it left you a function, but it has a hole, a missing piece there. This at x equals -2 is a jump discontinuity because the graph jumps from one row to the next. And at 0, there is a vertical asymptote, so this is an infinite discontinuity. And over here, we have two different y values, so we're at a jump discontinuity again. So those are the different types of discontinuities. And we'll talk about how to calculate those momentarily. So some other terminology that we need is if you ever see x arrow and a number with a little negative exponent, or x arrow and a number with a positive exponent. That means you look at the graph and you're looking at it from the left. So you're looking at basically one half of a graph. And if it has a little plus exponent, that means you're looking at it from the right. Like back on this example up here, talk about x equals -2. X equals -2. If we go, instead of saying equals -2, if we say go to -2 from the left, where's the y value going? Well, that y value is going up to 2. So f of x would be 2. But if we talk about it from the right, you follow the graph, it's at whatever that y number is, maybe 1/2 or something. So 2 from the right is different than 2 from the left. And if there's not a little exponent at all, that means we want from both sides, from both directions. We have to look from the left and from the right and determine what it's doing. So let's look at this first example here on example 2. 0 from the left. 0 from the left means go towards, when x is 0, what y number is that? And that is a y number of 2. And then the next row says, as x goes towards 0 from the right. So trace the graph, go back to 0 from the right side, we're up at a y number of 3. And this thing, so from the left and from the right, what's the y value doing? Well, they're not going to the same number, so it does not exist. D-N-E for does not exist. They have to go to the same number, and that number is our value. On the second one, as x approaches 2 from the left and from the right, we're at a y value of 4. That means that as x approaches 2, the y value is approaching 4. Now, that's different than f of 2. F of 2 is where the solid dot would be. F of 2 is 2. So evaluating a function, you look for the solid dot. But as x goes towards a number, you look at what the y value was headed to. What y value was it trying to be? And this one, as x approaches 0 from the left, we've come from the left. If we trace our graph, we're going down forever. So we would say x is approaching -infinity. F of x is approaching -infinity. As we go to 0 from the right, we're going up forever, so x approaches infinity. And since the left and the right are not the same value, this does not exist. D-N-E. And let's move on to the other side. Now, to determine from an equation, or from a function that's given, they're written out analytically, to determine whether there's a discontinuity, we need to know, can the denominator ever be 0? If the denominator is ever 0, the function is discontinuous, because we're not allowed to divide by 0. So, I look at this first one. Now it says, and the way we solve it, we're going to factor it in a second, and then if anything cancels, we have a removable discontinuity. If it doesn't cancel and the denominator is 0, there's an infinite non-removable discontinuity there. So looking at this first one, I notice if I let x be 0, I have a denominator of 0, so it is discontinuous. Discontinuous at x equals 0. Now, is it removable or non-removable? Well, that depends on whether we can factor this or not. So let's look at what we have here. We have, if I factor out an x, because there's a greatest common factor of x in the numerator, that would be 4x plus 1. If I factor out an x in the denominator, well, I can't factor out, sorry. There's just an x in the denominator, and then I can cancel that out. If I canceled it and divide numerator and denominator by x, I have just removed that discontinuity from the problem. Now there's no longer a denominator to have to worry about, so it is removable. It's a removable discontinuity at x equals 0. On the next one, if x plus 4, can that ever equal 0? Yes, when x is negative 4, so it is discontinuous, and at x equals negative 4. Now, at negative 4, is it removable or non-removable? Well, let's factor the numerator. We factor the numerator, and we look at what multiplies to give you 4 that adds to give you 4. And that's positive 2 and positive 2. Nothing cancels, so it is a non-removable discontinuity. Non-removable at x equals negative 4. So if you can remove it, it's removable. If it can't remove it, it's non-removable. Moving on to the next one. I look at the denominator, and can that denominator ever equal 0? Well, no, it's just 2. There's no issues on that one, so that is a continuous graph. It has no discontinuities. Continuous. And we don't have any removable or non-removable. It's continuous. So let's move on to the next one. Can this denominator ever be 0? Yes, at x equals negative 5, so it is discontinuous. Now, is it removable or non-removable? Let's factor the top and see. I know it's x plus 5 in the denominator. What multiplies to give me negative 15 that adds to give me 2? Well, it'll be positive 5 and negative 3. The x plus 5's canceled, so I remove them. The graph is going to look like the line of x minus 3, but with the hole at negative 5. So this is removable at x equals negative 5. Whatever made that denominator 0 is discontinuous because you can't divide by 0, but we were able to take it out of the problem, which left us with just the line x minus 3 is what the graph will look like, except for the hole. So on the next one, can this one ever be equal to 0 in the denominator? Well, I'm not sure in the current form, so let's factor. That would be x and x. What multiplies to give you negative 6? That adds to give you positive 1. So positive 3 and negative 2. So it is discontinuous whenever x is negative 3 or x equals 2. Discontinuous. Now, can anything cancel? Well, let's factor the top. Multiplies to be negative 6 still, and adds to be negative 1 would be negative 3 and positive 2. So nothing cancels, so whatever made the denominator 0, those are vertical asymptotes when it doesn't cancel. So you end up with x equals negative 3 and x equals 2. Those are non-removable, I should have said in first. So non-removable discontinuities, which means we have vertical asymptotes at those two values, at those two x lines. And the final one in this section, let's factor that denominator. If I factor out an x, I get x squared minus 4. So before I even do any more factoring, I notice I have a 0, so I do have a discontinuity. The denominator can be 0. The question is, can it be canceled or not? So on the top, let's factor out an x squared. And if I factor out an x squared, I'm left with x squared plus 1. That can't be factored any farther because it's a sum of two squares, only a difference of two squares, which, speaking of, we have a difference of two squares, so this could be factored farther. X plus 2 and x minus 2. So now, looking at my denominator and my numerator, I see a factor of x that I can, this had two x's, x times x, and I can take out one of the x's. So I had a removable discontinuity at x equals 0. None of the others cancel, so I have non-removable at x equals positive and negative 2. And now let's talk about piecewise. On piecewise functions, to be continuous, we have to check from the left and from the right, and anywhere where the graphs switch, basically. So we're going to look from the left and from the right, and then overall on this one. So on this first one, if it says as x approaches 0 from the left, well, if I look up here, this says x is smaller than or equal to 0. This says bigger than 0. Bigger than 0 are numbers on the right side of 0. Smaller than 0 is a number on the left side of 0. So we have to plug it into the top to get less than 0. To check from the left, we're looking at the top for numbers smaller than 0. So 4, and we're plugging in 0. So 4 minus 0 squared is 4. From the right means check numbers bigger than 0, which is the second row. So I plug in 0 here, sorry. 64 minus 0 plus 0 is 64 inside the cube root. The cube root of 64 is 4. So from the left was 0, from the right was 0. So that means overall, as x goes to 0, from the left at 0 we get 4, from the right we get 4. So overall at 0, we are approaching 4 from both sides. Now, this one should have said, we're talking about the g function here, so that should say g. As x approaches 3 from the left, well, I'm looking where 3 is. Here's 3 and here's 3. So from the left means numbers smaller than 3. So plugging in 3 is going to be on this middle row, this one. So that is negative 5 times 3, which is negative 15. From the right, when it has a little plus and the exponent, that means from the right, that'd be numbers bigger than 3. So that's this bottom row here. So plugging in 3 on that one, 18 over 3 minus 3 squared is 6 minus 9, which is negative 3. So overall, there's not a value as x approaches 3. But now it asks about as x approaches 2. Well, as x approaches 2, and it doesn't have an exponent, so that means from the left and from the right. Oh, negative 2, sorry. So negative 2 from the left is the top row. So x approaches negative 2 from the left. What's going to happen? G of x. Wait on my board to catch up with me. Wait, one more time. Okay, g of x is going to be approach. Well, let's see what it gets to. If I plug in negative 2 there, negative 2 minus 2 times negative 2 squared. Well, that's exponents first is 4. So that is negative 2 minus 2 times 4 is 8. So negative 10. So the absolute value of negative 10 is positive 10. Whoops, that's only for this one. We're not here yet. We've got to check from the left and the right first. So now I need to check from the right. From the right of negative 2 means bigger than negative 2, which is this one right here. It says x. Negative 2 is less than x. If you turn that around, that's x is bigger than or equal to negative 2. So if we plug in negative 2 on that row, as x approaches negative 2 from the right, g of x approaches, well, from the right, that's negative 5 times negative 2. Negative 5 times negative 2 is still 10. So from the left was 10. From the right was 10. So that means this answer is 10. And the final one here. This one has 4 rows. As x approaches negative 1 from the left. Well, that looks like this. I see negative 1 here, negative 1 here, and negative 1 here. We've got 3 different rows that all have negative 1. Well, from the left means numbers smaller than negative 1. So that's the top row. Negative 1 squared is positive 1. Numbers from the right means numbers that would have been bigger than negative 1, which is this part right here. So we plug in negative 1 there. Negative 1 absolute value is positive 1 times 2 is 2 minus 1 is 1. Now, this one spot right here, that's just like a solid point. So what we had going on is we had a parabola that had ended it. The parabola, we stopped drawing at a y value of 1. We pick up the next graph with a absolute value at 1, negative 1, and has the same y value of 1. So this is at x equals -1, the y value is 1, but at -1 itself, we're up here at 3. So this was just one little point, but from the left and from the right, we're both 1. And then the final one wants to know what happens at 2. Well, 2 is switching between these two rows. So we got to plug in 2 to both of them. 2 times 2 is 4 minus 1. You get 3. So from the left, 2 from the left goes to 3. 2 from the right, plug in 2 to this row. 5 times 2 is 10. 10 plus 6 is 16. Square root of 16 is 4. So one side is 3, one side is 4. Since those do not agree, there is not a value. This does not exist at that. The y values do not approach the same number. And that takes care of pretty much everything you need to know to be able to do assignment 1.6. Good luck to you.